Hello dear students, today we are going to talk about the topic single phase transformer. These are the pictures you must have seen on the roadside. This is single phase transformer. This is normally distribution side transformer, which the pictures I have shown over here. Now let me define transformer first. What do you mean by transformer? Transformer basically is a static device that transforms power from one circuit to another without change in frequency. The word transform is important over here. It is just not transfer of energy, but it is transformation of energy. Now why the term transform is used, I'll be elaborating on it a bit later, but for the time being just remember it's a device, it's a static device that transforms power from one circuit to another without change in frequency. As per Faraday's laws of electromagnetic induction, there are three things which are necessary for induction of EMF. One is conductor, second is magnetic field, and third is relative motion. The moment I say relative motion, it means it can be conductor which can be moving, or it can be magnetic field which can be moving. When it is conductor which is moving, the induced EMF is called as dynamically induced EMF, and when the magnetic field is moving, it is called as statically induced EMF. Another way to put it up is static or dynamic. Both these words are basically with reference to the conductor. If conductor is static, it is statically induced EMF, and if conductor is moving, it is dynamically induced EMF. Now, when just imagine there is a conductor placed in a uniform magnetic field, and the flux lines are cut by the coil. So there is an induction of EMF by Faraday's laws of electromagnetic induction. So E is equal to N d phi by dt. Now if at all this coil has got one more coil placed near this coil, irrespective of the fact that the another coil is not supplied with any voltage and there is no current set up in it, just because the flux lines which are flowing through this particular first coil are getting linked with the second coil, there is an induction of EMF in the second coil. So this particular EMF induced in the second coil is what is called as mutually induced EMF. So statically induced EMF and mutually induced EMF, let me again talk about it. Statically induced EMF means when the voltage is applied to the same coil, current is set up in the same coil, and because of d phi by dt, the change in flux, there is the change in flux d phi by dt, that means change in flux upon change in time. Because of this, it will be the EMF induced in the first coil. This is what is called as self-induced EMF. Another is when one more coil is kept in the neighborhood of this first coil, this flux linking with the second coil, there is an induction of EMF in the second coil. This is what is called as mutually induced EMF. So when I say mutually induced EMF, that particular coil is not fed with any supply, there is no current set up in it, despite there is an induction of EMF, and that is what is called as mutually induced EMF. Now when I talk about a transformer, basically constructionally there are three things. One is primary winding, the winding which is supplied by a voltage. Secondary winding, the winding which is loaded, that means load connected to the winding is the winding which is called as secondary. And third thing is the core means the substratum on which this winding is laid. So three things: primary winding, secondary winding, and core. There is nothing like primary or secondary written on a transformer. So it is basically as per the load requirement that one has to decide whether which particular side will be used as primary and which particular side will be used as secondary. So primary winding is the one which is supplied, and secondary winding is the one which is loaded. Now when I talk about core, basically it should be made up of very good magnetic material, which should have, when I say good magnetic material, which should have low reluctance and high permeability. So this is how a symbolic representation of a core and a transformer. You can see there is a core, and there are two windings, one is primary and another is secondary. Now if you see the Faraday's laws of electromagnetic induction, I just discussed few minutes before that EMF induced in the primary winding will be self-induced EMF because sinusoidally varying voltage is fed to the primary, sinusoidally varying current is set up in it, and because of that sinusoidally varying flux is set up in the primary winding. Now this causes self-induced EMF even at the primary winding. The flux linking this flux linking with the secondary winding produces EMF in the secondary winding. That is what is called as mutually induced EMF, because there is no supply given to the secondary winding, there is no connection between primary and secondary winding electrically, but the flux linking from primary to secondary induces a flux in the secondary winding, and that is why this is called as mutually induced EMF. So E1 and E2, where E1 is primary induced EMF and E2 is secondary induced EMF, the difference between E1 and E2 is E1 is self-induced EMF and E2 is mutually induced EMF. Both these EMFs E1 and E2 oppose V1 as per Lenz's law, that is they will always oppose the very cause producing it. Let me talk about classification of transformer now. There can be different bases for the classification. The very first basis, let me talk about the difference in the voltage levels. So if at all primary voltage is greater than the secondary voltage, that means V1 is greater than V2, we call it as step down transformer. And if at all vice versa, that means if at all secondary voltage is greater than primary voltage, we call it as step up transformer. So stepping up or step down is actually related to voltage. Second basis for classification is power handling capacity. So if at all the voltage levels those are handled are greater than 33 kilovolts, or if I talk about the capacity or rating, it is greater than 200 megavolt amperes, this transformer is called as power transformer, and below that these are called as distribution transformers. So if you remember the very first thing when I talked about transformer, these are the three pictures of distribution transformers. So these are very small rating transformers, these are distribution transformers. Okay, so let me come back to again we were talking about classification. So first classification was on the basis of voltage, second was on the basis of power handling capacity, third is on the basis of construction. So on the basis of construction there are two types, one is called as core type and another is what is called as shell type. If you see the diagram over here in 1.3, you can see when majority part of the core is covered by winding, it is called as core type, and when majority part of winding is covered by core, it is called as shell type. So the first diagram is of core type and the second diagram is of shell type. Now let me again have this chance to specify over here is, whenever I want to put any concept of transformer or define any terms in it, I'll be always using this core type transformer to explain it. But practically speaking, whenever even there is a small transformer which is to be manufactured, normally anybody will focus on the second type, and that is shell type. The reason obvious over here is there will be a leakage flux which will be less in this particular type. So normally anybody will go for shell type rather than core type, but whenever I want to tell you any concept regarding transformer, any working principle regarding transformer, I'll be always sticking to the first design, and that is core type. Okay, so let me again proceed further for EMF equation of transformer. We have EMF equations for every electrical machine. Let me elaborate on what is EMF equation of transformer. Before that, let me first just explain about a few terminologies that I'll be using in this EMF equation. Very first is phi m. Phi I'll be using always for flux, and m means the maximum value of it. So phi m is maximum flux in the core in Webers. Bm is maximum flux density in core, that is in Weber per meter square. N1 N2 are number of turns on primary winding and secondary winding. As I've already said, whenever suffix 1 will be used, it will be regarding primary. Whenever suffix 2 will be used, it will be regarding secondary. And whenever I use the suffix 0, it is always for no load. F is the frequency input current, that is always in hertz. As far as India is concerned, our frequency of the supply is 50 hertz. Okay. Now if you see this diagram 1.4, you can see when sinusoidally varying voltage is applied to the primary, sinusoidally varying current is set up in it, and because of that sinusoidally varying flux is set up in the core. So sinusoidally varying flux, you can see the sine wave of the flux. On x-axis we say it is theta is equal to omega t, and on y-axis I'm showing flux. So variation of flux with time, if you see, let us say I'm considering only that 1/4 of the time period. So if at all I want to tell you about the average change, average EMF per turn, it will be d phi by dt. And d phi by dt means change in phi upon change in time, so it will be phi m minus 0 upon t by 4. So you can see over here, as per Faraday's laws of electromagnetic induction, EMF per turn will be equal to d phi by dt, and the average value of this d phi by dt will be equal to phi m upon t by 4. Now if I substitute 1 upon t as frequency, and this 4 will be going into the numerator, so it will be 4f by m. Now this is the average value, but always the value normally we consider in case of any electrical systems is always an RMS value. So root mean square value. Root mean square value means that steady DC which when passed through a given circuit for the same amount of time will produce the same heat. So that is what is called as RMS value. So to convert this average value into RMS value, we have one thing what is called as form factor. So form factor is basically for standard AC is 1.11, and form factor is actually the ratio of RMS value and average value. So knowing the average value, you can find out the RMS value. So that is 4.44. Okay, and so to convert this average value into RMS value, we are multiplying this 4f phi m by 1.11. So this is 4.44 f phi m. If now I multiply this EMF per turn value by primary turns, I'll be getting EMF of primary, and if at all I'm multiplying this by N2, I'll be getting secondary induced EMF. So E1 is equal to 4.44 f phi m N1, and E2 is equal to 4.44 f phi m N2. If I divide this first equation by the second equation, I get E1 by E2 is equal to N1 by N2. Now another thing is in transformer V1 I1 is equal to V2 I2. So V1 I1 is equal to V2 I2 means the KVA rating is same for primary as well as secondary. So V1 upon V2 is equal to I2 upon I1. So I can write the same ratio now as E1 upon E2 is equal to N1 upon N2 is equal to V1 upon V2 is equal to I2 by I1. To put it in another way, I'll say in the transformation ratio, everything is 1/2, may it be turns ratio, may it be voltage ratio, may it be EMF ratio, but except for current, everything is 1/2, and the current is 2/1. Now let me proceed for transformer on no load. So when I say transformer on no load, the secondary is open circuited and there is nothing, or another way to put it up is secondary circuit is open means there is no load connected over there. So that is what we are going to discuss now, that transformer on no load. Now ideally speaking, when you talk about in a generalized way, when there is no load connected, you expect that nothing is drained from supply. But whenever transformer is connected anywhere, if at all, even if there is no load connected on the secondary, there will be certain current drained from the supply if at all supply is on. So this particular current which is drained from the supply when the supply to the primary is on, despite the secondary is open circuited, this particular current is for the core losses and for magnetization of the core. So I0, that is no load current, is basically for the core loss and for magnetization of the core. So you can see I0 is equal to IC plus IM. Okay, so yes, And when I talk about the power, this power will be equal to, again the suffix 0 indicates that we are talking about no load condition. So W0 is equal to what is primary voltage? It is V1 multiplied by it is no load current I0 multiplied by it is cos phi 0. Okay, so the wattage that will be there will be whatever is the primary voltage multiplied by whatever is no load current, where no load current is the phasor sum of core loss component and magnetizing component, multiplied by the no load power factor. No load power factor actually is very low, for example 0.2, 0.3 like that. So this value is actually very low. Okay, so if you see the phasor diagram is like this. You can see the x-axis is phi, the y-axis is you can see V1 is shown and exactly 180 degree phase shift it is shown E1 and E2. So as per Faraday's laws of electromagnetic induction, E1 and E2 both should oppose the cause producing it, so they are shown exactly 180 degree phase shift with V1. Okay, the core loss component will be in the same phase as V1 and the magnetizing component will be in the same phase with IM, and the resultant of IC and IM is I0. So just have a look on that I0. It is phasor sum of IC and IM. The moment I say phasor sum, the difference between an algebraic sum and a phasor sum is, when it is algebraic sum, it has to be 2 plus 2, which is 4. But in case of phasor sum, 2 plus 2 can be 0, 2 plus 2 can be 4, 2 plus 2 can be minus 4. Okay, so that's the difference between phasor sum. Another way to put it up is always the addition is done on a rectangular. Okay, so you can see the line parallel to IC is drawn, the line parallel to IM is drawn, and the diagonal of the rectangle is I0, and this is what is called as no load current. Okay, so this is about the no load phasor diagram. So if at all asked to you, you should be able to answer how transformer behaves on no load. So in any appliance where the transformer is there, even if smallest transformer is there, it is going to drain some current irrespective of the fact whether it is loaded or not. If it is supplied, it will be draining some current from the supply to magnetize the core and to have the core loss. Okay, yes. So now let us proceed further for transformer on load. Now when transformer is loaded, see, you can see the secondary circuit is now completed. There is a load connected to the secondary. So again we'll start with that alternately varying voltages supplied to the primary. Alternately varying current will be set up in the primary, that will cause alternately varying flux set up in the primary winding, which will produce E1 over here. This flux linking with the secondary will cause E2, and now the difference between no load and loaded condition is this E2 is now going to set up an I2 which will be fed to the load. Now the moment I say I2 is there, N2 is there, so N2 I2, that means secondary MMF, this N2 I2 will try to produce its own flux now in the opposite direction. But this is not tolerated, because transformer is supposed to be a constant flux machine, so whatever is the flux in the machine should be maintained constant. So to nullify this N2 I2, some more current is drained from primary. This is actually from primary, but it is induced because of the secondary, so it is called as secondary reflected current, so it is called as I1 dash. So N1 I1 dash is equal to N2 I2. Another way to put it up is, to compensate for N2 I2, it is N1 I1 dash. So when transformer is loaded, the current drawn from the primary has got two components. One is called as secondary reflected current, and another, as we had already seen, it is no load current I0. So I1 is a phasor sum of I0 plus I1 dash. Okay, you can just see the explanation given over here. Yes. Now let me talk about the phasor diagrams. You can see over here, when I say transformer is loaded, it can be resistive load, it can be inductive load, or it can be capacitive load. So let me talk about the very first one, the no load phasor diagram remaining same, that phi on x-axis, V1 on y-axis. Opposing to that is E1 and E2. Then it is I0, which has IC as component in phase with V1, and IM as component in phase with phi. But now it will be a second. When I say resistive load means V2 and I2 are in the same phase. So I have drawn that I2 is in phase with E2. Okay, so exactly with the same magnitude but in the opposite direction, it will be I1 dash, and this I1 dash and I0's phasor sum will be I1. Okay, similarly when I talk about inductive load, again the basic things remaining same, that phi is x-axis and y-axis is V1, and E1 and E2 are opposing to it, so exactly 180-degree phase shift. Then I say just because it is inductive load, that means current is lagging behind, so I have shown this current lagging behind E2. See, I2 is lagging behind E2. Okay, lag and lead are always in the anti-clockwise sense. So whenever I say something is lagging, it has to be in anti-clockwise sense, or when I say it is leading, it has to be in the anti-clockwise sense. So you can say in the anti-clockwise sense, current is behind the voltage. Now exactly of the same magnitude but in the opposite direction, we will be having I1 dash, and I1 dash plus I0 is going to give you I1. Similarly, phi as the x-axis, V1 as the y-axis, E1, E2 in the opposite direction, exactly 180-degree by Lenz's law, I0, and then it will be I2, which will be leading in the anti-clockwise sense from E2 by certain angle, phi 2, and exactly of the same magnitude but in the opposite direction, it will be secondary reflected current, that is I1 dash, and the phasor sum of I1 dash and I0 will be giving you I1. Okay, one more thing is this angle between V1 and I1 is phi 1, the angle between E2 and I2 is phi 2, and the angle between V1 and I0 is phi 0. Okay, so angle between V1 and I0 is phi 0, angle between V1 and I1 is phi 1, and angle between I2 and E2 is phi 2. So there are three different phase angles over here in transformer. One is phi 0 no load power factor, phi 1 primary power factor, phi 2 secondary power factor. So which particular power factor is to be taken while deciding about the rating of the transformer as VI cos phi? So somebody will say I'll take phi 0, somebody will say I'll take phi 2, somebody will say I'll take phi 0, phi 1, phi 2, anything can be taken. So normally instead of having this dispute, what we normally do is the transformer is rated in kVA and not in kW. So this is one of the reason that in the transformer there are three different power factors. So normally a transformer is rated in kVA and not in kW. This is one of the reasons why it is rated in kVA and not in kW. We'll switch further to equivalent circuit of transformer in the next lecture. Okay, thank you.